Bueno, esta primera clase que vamos a hacer va a ser sobre Irrigation Systems. Si es necesario, haré aclaraciones en castellano. This chapter is chapter 19 of the book and is written by Luciano Mateos. The area dedicated to irrigation in global agriculture has increased around 6 to 7 times since the start of the 20th century. Here we see the increase up to the 50s were more or less slow, and then it increased very rapidly. And today we have more than 300 million hectares of area equipped for irrigation. The greatest increases have occurred around in the South Asia and East Asia, and partly in North America. In other areas, the increase has been moderate. In Europe, the main countries with irrigated area are Italy, Spain, and France. Spain has the highest area, more than 3 million hectares irrigated, but the area equipped for irrigation, irrigable area, is around 3.5 million hectares for both Italy and Spain. Other countries have much lower areas for irrigation. In Spain, since the year 2000, the increase in irrigated area has gone from a little more than 3 million hectares to around 3.5 million hectares. Globally, around 17% of agricultural area is irrigated, but around 40% of crop production comes from irrigated area. To irrigate, we use mostly surface water, around 62%, and then only 38% comes from groundwater. Irrigation is or consumes around 70% of water withdrawals from rivers or groundwater, but irrigation is responsible for around 90% of consumptive water use. Irrigation systems might be classified according to different criteria. For instance, we might distinguish between collective versus individual irrigation systems, or we can distinguish between systems based on gravity versus pressurized systems that would include the sprinkler and drip irrigation. Gravity systems are basically surface irrigation systems. Collective irrigation systems, which means that we have many farmers using a common infrastructure for irrigation, might be organized according to different rules. The best or the most flexible organization of irrigation systems is the on-demand irrigation. In on-demand irrigation, the farmer decides the date of irrigation, the rate of irrigation, and the duration of irrigation. So the farmer has complete flexibility for applying irrigation anytime he decides to do. On arranged systems, before any irrigation, it has to be agreed between the farmer and the water authority. So each irrigation has to be agreed. So the water authority allows the farmer to irrigate at a given time for a given duration. A more strict organization is the so-called fixed rotation. In fixed rotation, the water authority organizes the allocation of water on a fixed schedule. For instance, the farmer may receive water a single day in the week, only one day every week. And then the farmer can decide if irrigating or not. But the farmer cannot irrigate on other days of the week. The main irrigation methods are shown here. An example of drip irrigation, an example of sprinkler irrigation. This is a hand move lateral. So when we finish the irrigation in this area, we move this lateral to another place and apply another irrigation. This is a surface irrigation system. In this case, it's furrow irrigation coming from a perforated pipe. In Spain, there has been a huge change in the importance of the different irrigation methods. The sprinkler irrigation has not changed much during the 21st century, but there has been a decrease in gravity system accompanied by a huge increase in localized irrigation, in many cases dedicated to tree orchards. This shows the patterns of wetting for different types of irrigation systems. In the case of localized systems, like in drip irrigation, the emitters are wetting a very small fraction of the soil area. So not all the root volume is wetted. In the case of sprinkler or furrow irrigation, most of the soil is going to be wetted, but in furrow there is a higher concentration of wetted area below the furrow, less water infiltrates into the ridges, but in sprinkler irrigation the infiltration is more uniform in the field. The localization of irrigation is also related to the timing of the application, the infiltration, and the uptake. Look at this. In drip irrigation, we typically apply these segments indicate the time when the irrigation is operating. So in drip irrigation, we are applying frequent irrigations. We are applying many irrigations with rather short durations. The phase of infiltration occurs later, but it's occurring during a rather short period, but in many events. Uptake, of course, root uptake is occurring all the time. The same happens if we irrigate using a sprinkler or surface irrigation. Uptake is always occurring. But in this case, the application and the infiltration is only occur in very separated events. So from one application to the next, we have a long interval that applies to both sprinkler and surface. The periods of infiltration are also occurring in very separated intervals. Okay, surface irrigation, which was the most common irrigation system in Spain since the start of irrigation systems in the 50s, usually is good for applying large irrigation depths. It requires leveling of the soil, so in general will only be adequate for rather flat land. The main concerns in surface irrigation is the risk of soil erosion if the flow rate is too high, and the uniformity of irrigation. There are two main types of surface irrigation. One is furrow, when we have partial soil wetting. Only a fraction of the soil surface is wetted, as you can see here, for furrow irrigation. In border irrigation, we build dikes around strips of the land, and the whole strip is wetted, is flooded. In the case of zero slope, we talk about level basins. That is the typical case for rice. But remember that the main concerns here are soil erosion if flow rate is too high, and the uniformity of irrigation. This graph shows the diagram of surface irrigation, where we plot the time that goes from the start. We put 0 time at the start of irrigation, the moment when water starts entering the field. If we plot time versus the distance that the water has advanced in the field, we have the advance curve. So at this moment, the water reaches the end of the field. Sometime after that, we will cut the entry of water into the field. This is called the cutoff, time of cutoff. Sometime after that, we will start to see that water disappears from the soil surface, and that marks the recession curve. So the recession curve marks the time when water disappears at different distances from the start of the field. Okay? So the time that goes from the advance curve to the recession curve is the opportunity time. In other words, is the time that the water can be infiltrating into the soil. The longer this time, the higher the infiltrated water will be. So we can distinguish different phases during the surface irrigation. We have first an advanced phase, which is the time from the start of irrigation until the water reaches the end of the field. Then we have a wetting phase, which is the time from the end of the advanced phase until the depletion phase starts, until the time of the cutoff. Then we have a depletion phase from the time of cutoff until the start of recession, until we see that water disappears at the beginning of the furrows. And then we have a recession phase during which the water disappears from the soil surface. These curves define the maximum amount of water that can be infiltrated in the different parts of the soil. Therefore, they determine what is the maximum uniformity of the surface irrigation. This is an example of furrow irrigation where water is diverted from an earth canal here. So water enters, and the farmer can regulate how much furrows you are irrigating at the same time by closing or opening different areas of this dike. These are other possibilities for diverting water from the canal. This is the case of using siphons. You put the siphon, you put at least one siphon for each furrow. And in this case, this is very common in Spain. This is a so-called plastocanal pipe, which is perforated at distances meeting the inter-row distance. So each hole serves one furrow. This is a cotton crop. This is a tomato crop. and the water is diverted to the different furrows using siphons. In this case, they use several siphons for each furrow. Well, what factors determine the uniformity in furrow irrigation? Ideally, we would like to have a 100% uniformity of irrigation. That would mean that all the places in the field would receive the exact amount of water. But this is not the case in many situations. The level of uniformity in furrow irrigation depends on the opportunity time, which is the time that we allow water to infiltrate, the wetted perimeter, and that depends on soil characteristics and the shape of the furrows, soil infiltration rate, that depends on soil texture and soil structure, the slope and roughness, for instance, the presence of residues, and the slope, which we have introduced, that we have leveled the soil with, and it will depend on the management, for instance, on the duration of irrigation. It is a rather complex process, so reaching high efficiency in furrow irrigation is not that easy. In the case of border irrigation, the factors would be similar, because we also have the properties of the soil determining the variability of the properties of the soil determining the variability in infiltration. The second main irrigation system is sprinkler irrigation. This is a pressurized type irrigation system that is adequate for medium large irrigation depths and has the advantage of not requiring leveling of the land. The main limitations of sprinkler irrigation are those of wind. If we have a lot of wind, if wind speed is very high in our area, we will have problems of uniformity. And also, we can have problems of infiltration rate, for instance, in clay soils. Apart from that, a drawback of a sprinkler irrigation is that it requires high pressure and therefore will imply a high energy cost. This is an example of sprinkler irrigation using a hand move lateral. In hand move sprinkler irrigation, we move by hand the pipes and we connect all the pipes. We put the sprinklers one by one and we open the valve and start irrigating. After several hours, say 6-8 hours of irrigation, we close the valve, stop irrigation, and then we move the whole lateral, we move it to a different position. And then we apply irrigation in the different position. This means that we require a lot of hand labor to apply irrigation. Therefore, in this case, it is important to reduce the number of irrigations as much as possible. There is other type of sprinkler irrigation system that is the so-called solid set. In a solid set sprinkler irrigation system, the pipes are buried in the field, so we only need to put the sprinklers in place to irrigate. Sometimes we can have even the sprinklers already fixed in the field, so we don't need even to move sprinklers around. So if we have the sprinklers fixed in the field, we only need to open the valve to start irrigating or stopping irrigating. Therefore, we don't require much labor to apply irrigation. Sprinkler irrigation is based on different types of sprinklers. This is the most common sprinkler type for hand move irrigation, sprinkler irrigation systems. This is the impact sprinkler that moves around because of the flow of water impacting a hammer, and the hammer causes the sprinkler to rotate all around. The main factors that determine sprinkler irrigation uniformity are the layout, which means the spacing between sprinklers, the pressure distribution. If we have a very long lateral line, we will have a low pressure at the end of the line, the nozzle characteristics that determine the pressure and the relationship between flow and pressure. Here, it is very important the weather conditions, basically the wind, because a very strong wind will distort the area wetted by each sprinkler. But also the management, which means what is the duration of irrigation and what is the frequency and intervals, or in other words, the intervals of irrigation. Another type of sprinkler irrigation is the irrigation using machines. And the main example of irrigation with machines is the center pivot systems. This is a center pivot in Nebraska. Here in center pivot systems, we have a place, a central point where water is supplied to the whole structure. Water comes through this and moves through this pipe, and we have the sprinklers on top. One important concern in pivot irrigation systems is the avoidance of runoff. In this graph, we are plotting the application rate or the soil infiltration rate. The soil infiltration rate decreases with time after the start of irrigation like this. It decreases as long as the water infiltrates the soil. So it decreases to a so-called basal infiltration rate. Imagine that we are using a very high application rate. This is the time course of application rate on any given point. As the pivot arrives to a given point, the infiltration rate increases, and then it decreases again. If you see here, the application rate is exceeding the infiltration rate. Therefore, this shaded area means that that would be runoff. To avoid that runoff, we should have a curve like this one, like the red one. Why? Because the maximum application rate is around equal to the maximum infiltration rate. That means that we have to fix the application rates in the pivot systems to match the characteristics of the soils. This is shown here. If we apply the high application rate, would be the black line, we would have a large fraction of the field where the application rate exceeds the infiltration rate. So we would have a lot of runoff. If we reduce the application rate to this value, we would have only a very small area of the field where runoff would occur. So remember, in center pivot systems, it is important to sorry, I have just seen the question by Daniela. Repeat what the nozzle characteristics are. we have not mentioned nozzle characteristics. We only have said that the nozzle characteristics affect the sprinkler irrigation uniformity. Nozzle characteristics is basically the diameter of the nozzle and the layout and the mechanical design of it, but we are not entering into more details. Okay. Another type of irrigation machine is the linear move system that instead of taking water from a single point, takes water from a ditch, a canal, or a pipe that goes parallel to the field that we are irrigating. This system moves in this direction, okay? So it moves parallel to itself in this direction, and it will be irrigating this rectangle. It will be taking water from either a pipe going from one of the sides or a canal going all along in one of the sides. Clearly, well, this is a spray sprinkler. This is typically used in pivot or linear move systems. This is another example of center pivot irrigation. In this case, it is irrigating a rapeseed field. It is clear that pivot irrigation will be more adapted to fields that can accommodate a circular shape. On the other hand, lateral move systems will be more adequate for rectangular fields. Okay, the third irrigation system is, or third main irrigation system is that of localized irrigation. Localized irrigation can be used anywhere because it can be used with any type of orography or under any climate conditions. It is also very flexible in terms of amounts that you can apply with. So you can apply doses as small as a few millimeters up to, say, 50 millimeters. According to all the things we have been saying about the sprinkler irrigation or surface irrigation, it is clear that very low doses will not be adequate at all for surface irrigation. On the other hand, sprinkler irrigation using hand move systems will not be good for small irrigation amounts. Pivot systems can accommodate rather small doses, say 30 millimeters or around 40 millimeters. But the most flexible one for applying very small irrigation amounts is that of localized irrigation. As compared to sprinkler irrigation, one advantage of localized is that it requires less energy because of the lower pressure requirement. We can distinguish in localized irrigation between drip, where we use drippers, which are emitters that apply water using, we use drippers as emitters. Then we have micro sprinklers, and we can also have subsurface drip irrigation. Typically, localized irrigation is applied to permanent perennial crops like fruit trees, and only in some instances it is used in field crops, like in this case for maize. Here we see an example with fruit trees. we see the wetted area by each dripper. We can have the drippers inside the tube, the so-called inline dripper. So the dripper structure is built into the pipe, and this is the orifice where water comes from. This is another example of inline dripper. We see here the wetted area below. And in this case, we see a drip irrigation system. This is an almond orchard in the Cordoba province. And we see here a detail of, in this case, a so-called online dripper. So here the dripper is outside of the pipe. For some fruit trees, is more economic and more efficient, instead of using drippers, to use micro sprinklers, because we can increase the wetted area. One important concern when irrigating trees is that we need to wet a minimum soil area to keep the maximum transpiration of the trees. If the wetted area is too small, then the trees won't have enough water for transpiration. Therefore, in some cases, we need to use micro sprinklers to allow enough wetted soil area. As I said, we can also have drip irrigation with the pipes buried below the soil surface. This is a case of subsurface drip irrigation in olive trees. In this case, the pipes have been buried in between the tree rows in the middle, and we see here these wetted spots. That means that there is water flow from the pipeline, from the pipes to the soil surface. This is something that we don't want to occur, because then we are not saving water from soil evaporation. So ideally, if we install subsurface drip irrigation, we should see a dry surface. Of course, well, this is a detail of the pipe that we would be burying to apply subsurface drip irrigation. And this is an example of a plot where we have installed subsurface drip irrigation, and this is the plot after we have grown a wheat crop. One important problem with subsurface drip irrigation is that we cannot observe directly the emitters, so problems are detected usually too late. So we usually observe problems when we observe flooding of parts of the field. Well, the uniformity in drip irrigation systems depends on the pressure distribution. Of course, that will depend on the length of the laterals that we have in the field. In this case, it is important to consider the quality of the product of the emitters, because depending on that quality, the emitters can have a lot of variation in their characteristics and in their discharge rates. A very important concern in drip irrigation is the risk of emitter clogging. So if the water is not clean enough, the emitters will be clogging very soon. And this is something that we don't want. If clogging occurs, then the drip irrigation uniformity will be very low. Of course, uniformity will depend on management, on the duration of irrigations, the interval between irrigations, etc. To avoid emitter clogging, it is important to dispose of a filtering system. That would be critical to ensure the water quality to avoid emitter clogging. Well, if we want to know if an irrigation system is performing correctly, we can evaluate its performance. There are different ways where we can evaluate the performance of an irrigation system. Here we see, for instance, the example of surface irrigation, where we are irrigating a sunflower field. We see on top we have water that is infiltrating, and we see here that infiltration is occurring at different rates in different parts of the field. The longer the field, as we move from the water inlet, the amount of irrigation of infiltration is reduced because the opportunity time is reduced. And when the water reaches the end of the field, if the field is open, we will have to start runoff, that in this case is collected in a ditch. To evaluate irrigation by furrows or surface irrigation, we need to measure the flow rate into the different furrows, and we will need to determine the advance and recession curves along the furrows. In this case, we have somebody that moves along the furrow and measures the time it takes to reach different places in different distances along the furrow. We can also use flumes to determine the flow rate in different places of the furrow. This is something that farmers would not normally be able to do. In the case of a sprinkler irrigation, the evaluation requires measuring the flow rate from the sprinklers. That is very simply done just by putting a hose to close the sprinkler and then collect all the water that is flowing out. Then we need to install a grid of catch cans at a regular spacing. And then after irrigation, we measure the water collected in the different catch cans. And then we perform, or we calculate, the performance of the irrigation system according to the values that we have measured. Something similar is done for drip irrigation, but in drip irrigation, what we do is that we measure the flow rate using a timer and a small base with a given known volume. So we measure the time required to get a given volume of water. We measure the emitter discharge at different points in the field, and with these numbers we apply the calculations that we will see later. Here we see the main procedure for evaluating the main performance indicators for irrigation. And these main performance indicators are adequacy, application efficiency, and distribution uniformity. Let's see what is the meaning of these parameters. If we go to the field, for instance, a sprinkler irrigation system, and we measure the water collected in different parts of the field, then we plot starting from the highest to the lowest value. We order all the values by the amount collected. In this case, we have measured from 130 millimeters, and the lowest value has been around 50. And we assign to those the fraction, given fraction of the field. Then we plot here what is the average value that we have collected. And we also plot here the target value. We wanted to apply an amount of irrigation of 90 millimeters. But on average, we have measured 98.3. As we have ordered the different values, we go to the quarter, so the values that go from 0.75 to 1, and calculate the average of all these. We calculate the average of the low quarter, and the average of the low quarter is 73 millimeters. Okay, now with these three values, we can calculate the different performance indicators. The irrigation adequacy means the fraction of the field that receives more than the water that we wanted to apply. In this case, look at this. We wanted to apply, target was 90. We see that around 73% of the field is receiving more than this target amount. So the adequacy is 73%, which means that at least 73% of the field is receiving more than the target value. We also can calculate the irrigation adequacy for the low quarter. That means dividing the average for the low quarter, which is 73, divided by the target amount, which is 90. 73 divided by 90 is 81%. That is, the adequacy is very close to the adequacy in the field, which we said is 73. But we can also calculate the so-called application efficiency, and the application efficiency is the ratio of the target amount. Remember, the target was 90 millimeters, and the average irrigation amount, which was 98.3. By dividing the target by the average, we get a value of 87%. That is the application efficiency. But we also are worried about the distribution uniformity. We want, if possible, the distribution to be high. Therefore, if we have a very high distribution, we won't have a lot of water being, or a large area being over-irrigated, or we won't have a large area being under-irrigated. The lower Q, somebody is asking what is lower Q. Lower Q means the average irrigation in the quarter of the field receiving the less water. That is the I lower Q. And we use the I lower Q for calculating the distribution uniformity or the irrigation adequacy. In the case of the distribution uniformity for the lower Q, or based on lower Q, is the ratio of amount of water in the lower quarter divided by the average water applied. Remember, the average amount in the lower quarter was 73, and the average irrigation amount was 98. The ratio of those is 74%. So the application efficiency warns about the overall losses in the system. The adequacy tells us what is the fraction of the field that is receiving at least the amount of water that we want. So if the adequacy is close to 1, means that in no place of the field we will have water deficit. The distribution uniformity going or approaching 1 means that the whole field is receiving the same amount of irrigation. As the distribution uniformity gets lower, It means that that there are places receiving too much water and places that receiving less water than required. Apart from applying water to the field using the irrigation system, in many cases it is important to consider drainage systems because we need to remove the excess water not used by evapotranspiration, or leach salts. We will go back to that next week. For drainage, we can use surface drainage, which means opening shallow open ditches. Or we can use subsurface drainage, that are pipes or tiles that are buried in the field that will serve to dispose of the excess water in the field. These pipes or tiles might be buried perforated pipes or clay tiles. This is an example of surface drainage. In the Netherlands, we have here a large field, and in this case, this drainage drainage ditch marks the level of the water table. So the field here will be irrigated basically from movement from the water table. In Marismas del Guadalquivir, we typically see this system where we have these drainage pipes buried at rather deep, around 1 meter depth, and the drainage pipes dispose water or take the water to the drainage ditches at the end of the field. So we have these large drainage ditches that collect all the drainage water and remove them from the irrigated area. Well, not all the water applied by irrigation is used by the evapotranspiration process. The excess water goes either by deep percolation to groundwater, or by surface runoff, it returns to ditches, and from ditches to the rivers. The whole or the sum of deep percolation and surface runoff going out from of the fields are called return flows, as they return to the hydrological system. So if we save water in our field, that reduces the return flows to the hydrological system. In some cases, we can reuse the return flows either at the field or the farm or the scheme of the watershed level. So the water going out as surface runoff from a field can be collected by another field and be used there. This is an example of reuse of water inside a farm. We are irrigating tomatoes using furrows, very long furrows, and this is the tail of the furrows, and the excess water is being collected in this tail ditch, and we can pump the water back to the start of the furrows, to the inlets in the furrows. In that way, we can be reusing water continuously. So we are improving the irrigation efficiency in this field. But if we are not reusing this tail water, this water can go to another farmer, and the farmer can use it to irrigate their fields. So in the end, the irrigation efficiency at the scheme or at the irrigation area scale will be much larger than at the field level. So many times we improve the irrigation efficiency, the application efficiency at the field scale, but that does not improve the irrigation efficiency at the huge irrigation scheme scale. Well, thank you for attending this class. If you have any question,